Before we start on regression and correlation, I recommend you take a minute to jot down as much information as you can about these 5 key terms or phrases. Each of them relates closely to what we're going to be looking at today, and the words are important, your definitions are important. You may have some idea of what they mean, but you might find it difficult to put into words. The process of trying to put it into words is really helpful. If you don't understand what a word or phrase means, see if you can work out something about it by looking at the word and breaking it apart. Once you've done that, have a quick look at the section on the right, some claims which are potentially backed up by statistics. Maybe there's some very convincing looking graphs, maybe there's some correlation, but the claims do not quite ring true. Once you've got your list, come back to the video, we'll see whether your definitions tie in nicely with mine. The first one, bivariate data. There are 2 bits to this word, the bi and the variate. And as you might guess, bi stands for 2 and variate suggests variables, so 2 things that vary. It's important here to recognize that what we're dealing with is not just 2 different things that you happen to measure, but we're measuring data in pairs. In other words, we're not just going around asking a bunch of people for their heights and then going around again asking the same bunch of people for their shoe sizes. What we might be doing is asking an individual for both their height and their shoe size, and then we write them down together so that those 2 data points are connected. And we could represent them on a scatter graph, for instance, but it matters which height goes with which shoe size. If that's the sort of data you're dealing with, you have bivariate data. It's different to just 2 sets of data. Correlation. Correlation refers to the relationship between 2 things, and specifically the type of correlation that we look at is a measure of the linear relationship. This is important. When we look at 2 things that might be related, there could be all sorts of connections between them, but the product moment correlation coefficient that we're going to investigate and learn how to calculate is specifically a measure of the strength and the direction of the linear relationship between 2 variables. What we mean by a linear relationship is essentially how closely the data matches the next thing in our list, the line of best fit. The line of best fit is essentially if you represent your data on a scatter graph and then you draw a straight line through that data, the line of best fit is the best line you could draw, the one that most closely matches the relationship between the 2 sets of data. It's kind of like a 2-dimensional mean average, and you can describe it as the straight line which is closest to all the points. We'll talk more shortly about exactly what we mean by closest, because how you define distance becomes fraught with difficulties once you're in 2 dimensions potentially. The next 2 are both kind of connected to each other. One of these is more reliable, the other one is more useful. Interpolation and extrapolation are both a way of making predictions that your data cannot give you. But one of them is about making predictions within the set of data you have, in other words, within the range that you've investigated, and the other one is about making predictions beyond that range. As you can probably guess from the prefixes here, interpolation is inside the data range and extrapolation is beyond the data range. Now, interpolation is likely to be the most reliable. This will be like, let's say you measure the height of your grandchild on their birthday every year, but a pandemic hits and you're not able to visit them in 2020. So you've got data for every single year, their first 6 years of their life, and then you miss their 7th birthday. And you've got data for when they were 8 years old, 9 years old. And you could probably fill in the gap. If you wanted to complete your graph, you could have a reasonable prediction of how tall they would have been on their 7th birthday. That would be interpolation. And it's reasonably reliable, but it's not necessarily as useful. It's all very well to do things like predict how big the population of the world might have been 300 years ago, but what people are really interested in is how big the population of the world might be in 300 years' time, and that's a question we can't very easily answer. But that's, of course, the more interesting and useful question a lot of the time. We just have to be very careful if we're extrapolating. If you've got the height of your grandchild every year for the first 12 years of their life, and then you decide to use the relatively good mathematical model that seems to fit those data points and extrapolate it on to calculate how tall they'll be when they're 35, you might find yourself calculating that they're going to be 26 feet tall. So you want to be a little bit careful with extrapolation. Height is not the only thing which appears to be linear initially, but then a linear relationship breaks down. Even if it was a very good linear relationship, it may not be a linear relationship that persists. As you might have guessed, the 4 claims on the right-hand side are not necessarily true, but all of them indicate some sort of misconception based around the idea of correlation and causation. You'll very often see examples of this that are somewhat more subtle and therefore more dangerous. It might be that there is a strong correlation between absence from school and poor exam results. But often the conclusion drawn is that if you decide to take your kids out of school for the last 3 days of the summer term, then your child will therefore get poorer results in their GCSEs. There are other factors at play, generally speaking, in these correlation connections between things. For instance, ice cream and drowning. It's not that spending money on ice cream increases your chance of drowning. It's not even that being a bad swimmer makes you spend more on ice cream. It's probably more like if it's a nice hot sunny day, lots more people buy ice creams and lots more people go swimming in the sea, and therefore more people will drown. The larger your shoe size, the more money you earn. That's certainly true in my house, where my 5-year-old daughter and my 7-year-old son frankly bring in very little in terms of hard income, and me, with my slightly larger feet, seem to be making more money than both of them put together. But that's unlikely to be because of my shoe size. As you can imagine, there are other factors at play. In this case, age is the obvious one. Let's start by looking at an example of bivariate data. We've got paper 1 and paper 2 from a GCSE maths exam. And the question will be, is there any correlation between the two sets of results? What we're looking for is not some hard and fast rule about exactly how well somebody will do on the second paper based on their first one, but just to get a sense of whether there's a general trend. So, for instance, if you scored, let's say, 32 marks on the non-calculated paper, then you could be any one of these students potentially. You might have done well, you might have done poorly on the second paper. But generally speaking, if you were a very strong student, you're likely to have done well in both exams. And if you're a very weak student, then perhaps you did poorly in both exams. And overall, there's likely to be a general sort of trend. You could probably put a line through there and say that, roughly speaking, the data lies close-ish to that line. And that's essentially like a 2-dimensional mean average of this data. And it will give us a way of making predictions within the data, which we know will not be perfect, but they will be reasonably good, particularly if you've got a large set of data. They'll be useful for things like a student sits paper 1 and then they get ill and they have to miss paper 2, and the exam board has to make a prediction of what they would have got in paper 2. Now, it might be that paper 2 generally was found harder than paper 1 by most students. It might well be that the student who's sat paper 1 has got a very poor result, and you would expect them to get a poor result in paper 2. If they've got a very good result, they'd expect to get a good result in paper 2. And the algorithm will not be perfect for an individual, but it will, broadly speaking, give expected results on average across the population. So when we're looking for correlation, we are looking for the measure of the strength and direction of the linear relationship. We need to know whether this is a positive or a negative correlation. That's what we mean by the direction of the linear relationship. Is it the case that the better you do in one paper, the better you do in the other one, or is it vice versa? Depending on the content of the exam papers, you could conceivably imagine a couple of exam papers, perhaps in very different subjects, where students who do particularly well on one score rather poorly in the other one. Perhaps the two skill sets are somewhat opposed to one another. Those people who are good at big picture and out-of-the-box thinking perhaps struggle when it comes to attention to detail and precision, whatever it might be. In this case, as you'd expect, there appears to be a reasonably good positive correlation between the two. It's not perfect. If it was perfect, you probably wouldn't need paper 2 because you'd know what students were going to get in paper 2 before they sat it, so it's a fairly pointless exam to do. But given that the two papers are supposed to be testing some other underlying thing, the students in innate mathematical understanding and ability to apply it, it seems reasonable that there will be a correlation between the two. In this particular case, we would describe that as a positive correlation. We'll talk about whether you could call it strong or weak later, but generally speaking, it's a bit like thinking of something as likely or unlikely, or very likely or extremely likely when you talk about probability. There's only so far that descriptive words can take you, and people have different interpretations of those words. It's better if we can quantify exactly what we mean. So generally speaking, at A level, if you're asked to describe the correlation in words, you would use positive or negative, or perhaps no correlation. And you might use strong or weak if it's particularly obvious. You do occasionally. But generally speaking, the strength of the correlation is indicated by the number that you will calculate, which we'll get to shortly. But in addition to saying the mathematical phrase positive correlation, usually you'll be asked to interpret that within the context of the scenario being described. In this case, we're talking about GCSE maths exam results, so we'd expect a statement something like this. In general, this is a useful phrase because instead of saying something like all men are faster than all women, or men are faster than women, we can qualify that statement slightly and turn it from something which is false to something which is true. In general, men are faster than women. That essentially means that on average, if you pick a random man and you pick a random woman and you make them race, then the man will probably win. Maybe he has a 60% chance of winning. So it's not a hard and fast result, but it's certainly something that you could generalize about. And in this case, the generalization is that the better a student does in paper 1, the better they are likely to do in paper 2. It doesn't mean that they will do better. It doesn't mean that there are no students who buck the trend. It just means that in general, this is the trend you would expect to see. The other thing to mention is the names of the variables themselves. The independent variable, paper 1 in this case, is the one that will be plotted along the x-axis, and the dependent variable will be plotted up the y-axis. They're sometimes called the explanatory and response variables. To think about that, explanatory means this is the variable which explains or determines the other one. The response depends upon the original thing. So it may not necessarily be the case that the thing plotted on the y-axis depends upon the thing on the x-axis, but generally that's the assumption, that if there is a causal connection, then that's the direction it goes. In this case, that's why I've got paper 1, the first paper that's sat on the x-axis, and paper 2 on the y-axis. We're assuming that paper 1 has been sat and that we're wondering what happens with paper 2, then paper 2 gets sat, and we're wondering if the results from paper 1 have had any kind of impact on paper 2. It's unlikely, given that paper 2 happened after paper 1, that what you're going to get in paper 2 affects paper 1. But in reality, things tend to be more complicated. In this case, for instance, probably both of your results are likely to be influenced more directly by some third factor, like your mathematical ability and your understanding and your capacity to demonstrate that in an exam situation. Let's look at a few more examples just to remind ourselves what we mean when we talk about the different types of correlation. If we have a line of best fit on this graph, we would describe this as positive correlation because as one variable increases, the other one does as well. On the other hand, if we get a negative correlation, you can see this downward trend. So the greater one value gets, the smaller the other value gets. This will be a negative correlation. Have a quick look at these four and see if you can identify which of them you think is positive or negative correlation. See what kind of description you would apply to each. For the first one, I have no correlation. You might see places where you could put a trend line, a line of best fit, but there is not really any strong indication of any linear relationship here. The second one is positive correlation, sometimes referred to as perfect positive correlation. This would be something like a Hooke's law experiment in physics, where you increasingly pile on masses to a spring and you measure how far the spring extends. And it turns out that the spring will extend by a regular amount when you increase the mass by a certain amount. There's a very strong linear relationship between the two, and you can calculate the gradient and you call it the spring constant, perhaps. That's what we might refer to as a positive correlation that's either very strong or in some cases perfect. every single point essentially lies on the line instead of just very close to it. The next one here is a negative correlation, and then the one in the right-hand corner on the bottom is a positive correlation. So generally speaking, for those last two, there is a trend you can identify. Most people would agree that it seems to be a downward trend in the bottom left and an upward trend in the bottom right. Now we're going to look at how we can put a number to a correlation. If you take a quick look at these, you'll recognize pretty quickly some you would describe as strong correlation. In fact, there's an equally strong one over there, which just happens to be a negative correlation. And then some are more weak correlations, positive or negative. We have what we described as a perfect correlation. And again, that can be a perfect positive or a perfect negative correlation. The next thing we're going to do is put these on a scale, a numerical scale, just like we do with probability, where we go from impossible to certain. Any probability can be mapped onto a 0 to 1 scale. We do the same kind of thing with correlation strength, 0 to 1. But then we do an extra thing. So think about the 0 to 1 scale like a dial that you can turn up. You can pick any value between 0, which is no correlation, and 1, which is perfect correlation. But in addition to that, you have a toggle switch that can go either positive or negative. So our scale looks something like this. Perfect positive correlation would come out as a 1, and perfect negative will be a negative 1. And then the weaker the correlation, the closer it is to 0. The stronger the correlation, the closer it is to either 1 or negative 1. So think in terms of the size and the sign separately. The size of the correlation coefficient tells you how strong the relationship is, and the sign gives you an indication of which direction it's going. Notice it doesn't tell you the gradient, because it's limited to maximum of 1 and a minimum of -1. It's not going to tell you how steep the line of best fit is. For that, you need to calculate the equation of the line of best fit, which we'll get onto as well. But the sign in front of the number tells you whether the gradient is going to be positive or negative. So the next thing would be to see if you can predict what kind of number you would expect for each of these 7 scatter graph examples. What would you put down for the perfect negative correlation, the strong negative, the weak negative, etc., all the way through? See if you can guess a number based on this scale from -1 all the way up to 1. When you think you've got a number written down, unpause the video and we'll see if we agree. All right, here's what we've got. Well done if you managed to get similar-ish numbers. The scale should give you some clues. Roughly speaking, if we're looking at a correlation below 0.5, then yes, it may be statistically significant. In other words, it might well be unlikely to occur just by random chance, but it's not necessarily indicative of an extremely strong relationship. Whereas if you were investigating something like a physical law and you had a good experimental setup, then you should expect to find a much stronger correlation. If, for instance, you're measuring the time it takes something to drop through a viscous fluid, and you've calculated that there should be a linear relationship between the mass of the object and the time that it falls, then it might be that you would expect your graph to look pretty close to a perfect positive or a perfect negative correlation. And if it isn't, then there might be something more complicated going on that you've not taken into account. Here's a few other diagrams. Have a think about what kind of numbers you would expect to put on there for a correlation coefficient. Think about the size and the sign for each one. Pause the video at this point if you want to try jotting some down before I go through the answers. Okay, the bottom row, turns out all of those are a 0 correlation. Every single one. If you try to map a straight line to them, then there's no preference of whether it's positive or negative. Essentially, there's no right or wrong straight line you could put through them, and that's an indication that you shouldn't be trying to model them with a straight line. It doesn't necessarily mean there's no relationship whatsoever. It just means there isn't a linear relationship between the two. Clusters, in fact, like this one here on the right, they're really useful. That's what programs like Amazon and Netflix use to suggest new products or new movies to you based on your previous viewing habits or what you've shopped for in the past. they'll be able to put you on a multi-dimensional scatter graph with all the other people who've shopped, and then you'll end up in clusters. So if you've bought climbing shoes and a chalk bag recently, then they're going to start suggesting things like climbing rope and spare chalk, not because they know that you're a climber, essentially, but because you are now grouped with other people who've bought similar things, and if you buy this, you're likely to need this. You've probably been recommended the Year 2 A-level maths book if you've ever bought the Year 1 A-level maths book. It's not necessarily because Amazon knows they're part of a set, it's just because many people who've bought one have also bought the other one. Now, the middle row is quite interesting because most of these should be the same size, but the opposite sign potentially. Hopefully you got a positive 1 for those 3 on the right and a negative 1 for the 3 on the left. Interestingly, the one in the middle is kind of undefined. The problem with that one is it doesn't look like a zero correlation because everything lies perfectly on a line, and we've given that the name perfect correlation. So I don't really want to give it a 0, but on the other hand, it's not a positive correlation and it's not a negative. It's more like plotting your age and the number of fingers you have. Unless you get really unlucky, chances are if you plot age against number of fingers, you will find that you get a nice flat line. You have 8 fingers regardless of your age. Now, I would probably say that that means there isn't really a linear relationship between those two things. Because although I could very accurately predict how many fingers you have just by finding out your age, I also don't need to find out your age to predict how many fingers you have. So it's a bit of a different situation. And you might argue that it deserves a size of 1, but it doesn't deserve a sign of either positive 1 or negative 1. So it's undefined, and we'll leave that one. When we think about correlation and causation, we need to understand the difference between the two things. Correlation suggests that there appears to be some form of linear relationship between two things. Causation suggests that one of those things causes the other one, that there is some link, and that by messing with one of those things, you could impact the other one. Here's a bunch of things that you could plot on a scatter graph, and you would discover a surprisingly strong correlation. There is definitely some kind of connection between these. But there are various different forms that connection could take. In some cases, the thing on the left, the time spent traveling, for instance, determines the thing on the right. So if you decide to travel for a longer time, you will get further. In other cases, it might be that the thing on the right determines the thing on the left. Temperature is a good example of this. When it's a cold day, you wear warm clothes. You don't put on a woolly hat and gloves, and as a result, the temperature drops. That's not the order in which the causation works. BMI and miles cycled is a good example of one that kind of works both ways. So although the time spent traveling does go this direction and temperature and clothing goes this direction, BMI and miles cycled kind of produce a sort of feedback loop. So if you do lots of cycling, then your BMI is going to drop, your body mass index, a rough indicator of your level of fitness and healthiness. So if you are active and you go out cycling, chances are you're going to become more fit and healthy. On the other hand, the more fit and healthy you are, the more likely you are to choose to go out cycling. So both of them feed off the other, and you get a complicated sort of relationship between them. The cost of car insurance and the age of the driver, this one, of course, is likely to go the other way. If you are younger, then you're likely to have to pay more for your car insurance. Just getting cheaper car insurance does not automatically make you older. It's just an indication that perhaps you are older or safer. The number of books at home and attainment at school was an interesting example. I think Washington, D.C. school districts had a test at one point. They'd done a study and they discovered that there was a strong correlation between how many books you had at home and how well you did in school. So they thought, well, this is a quick, easy win. All we need to do is buy a bunch of books for the underprivileged families in the communities, and then suddenly we'll get a massive boost in school achievement. So they tried it out, and it had no effect whatsoever. It turns out buying books doesn't make people better at school. Having lots of books in the house was not the cause of students doing well. It was a side effect of the kind of families and the kind of backgrounds they were from. If you were from a higher socioeconomic group, and your parents were more likely to be college educated or have a university degree, then of course you're more likely to have books in the house. You're also more likely to have been read to at an earlier age. You might have heard twice as many words by the time you're 4 as people from a lower income and lower education background. And all of those factors are what drives students to do better in school. Providing some books doesn't really do the job. It would be like giving my daughter a larger pair of shoes because people with bigger shoes make more money. Doesn't quite work that way around. Now you should be able to have a go at the questions from exercise 4A. You can try a few of these, pick out a few that you want to have a go at, represent them on scatter diagrams if that's what they ask you to do, and think about how you can interpret the correlation and think sensibly about any potential causation within the context of the questions. Next, we look at the line of best fit. So we can think of this as a line which is as close as possible to all points. And in reality, what that means is that it will give us something like the two-dimensional equivalent of the mean. It's not surprising then that the mean of the x-coordinates and the mean of the y-coordinates should be a point on our line. It's the average of both of the things we measured, so that's going to be a point that belongs on our line of best fit. But then how you determine the slope of the line, once you know which point it goes through, that's the only thing left to find. We determine the slope by using a sophisticated method called the least squares method. We're trying to minimize the square of the distance vertically from the line to each point, which seems like a convoluted thing to do. But if you think about it, we have an independent variable along the bottom, and if you're doing a science experiment, it might be that that is the temperature at which you start your reaction. And then the dependent variable might be the amount of reactant you're able to produce. Now it's assumed that you have measured the temperature pretty accurately, but that perhaps the amount of reactant is going to have a bit of error in it. So typically you'll have error bars in your graph, and there'll be vertical error bars. You'll have, let's say, a data point here, and then you might have an error bar that goes up and down as far as a certain amount. And that suggests that if you've got a bunch of data points, each of them potentially has its own error bars, and they may all be the same size, they may be a bit different. And what we're trying to do is find a straight line that plausibly could go through or close enough to those lines so that the distance away, the amount of error required to make it a straight line fit, is as small collectively as possible. Luckily for us, we don't need to go through the mathematical process of finding that line because the calculator will do it for us. In menu option 6, the statistics option, you can do linear regression, which is a fancy way of saying you can find the equation of the line that fits your data. We'll look at an example of that next. So here we have a little bit of example data. We've got scores from the end of year 12 test and from the beginning of year 13 test, FA1 at the start of year 13, for a set of students. On your Casio ClassWiz calculator, you need to choose menu option 6, then choose option 2 for linear regression. That should say something like y equals a plus bx. That will allow you to enter data for your x coordinates and your y coordinates. You can ignore the percent sign. You don't need to type in 0.48. You can just put 48 for 48%. Just remember that the values you get out the other side will be percentages, even though you've not included the percent sign in the original data. Once you put your data in by typing numbers and pressing equals after each number you type in, then you need to press the options button, which is near the top left, OPTN, and then choose option 4, which is regression calc. Once you've done that, you should see 3 values appear on the screen. There'll be an R value, an A value, and a B value. It'll also say at the top y equals a plus bx. That'll remind you whether A is the gradient or the intercept and vice versa. So in this case, because of the format they've given you, y equals a plus bx, you know that the value they give you for A will be the y-intercept, B will be the gradient, and then the third value they give you will be R. And since it's neither A nor B, it must be the other thing, which is the product moment correlation coefficient. In other words, the size and sign of the correlation. This is the number that will tell you how well correlated that data is. So when you put that into your calculator, you should be able to get the values for A, B, and R. I'd like you to pause, write those down once you've found them, and see if you can answer the questions on this slide. And when you're ready, unpause, and we'll compare our answers. So here's what I get for the product moment correlation coefficient. I have R equals 0.785 to 3 significant figures. Looks reasonably good. It's a strong positive correlation. Now there's only a handful of data points, so we can't be absolutely certain that this is always going to hold up, but it seems like a reasonable starting point. As we would expect, there is a connection between Year 12 results and Year 13 results. Students in general, students who do better in Year 12 also do better in Year 13. And again, in general, but not necessarily for every individual, students who struggle in Year 12 will continue to struggle in Year 13. It is, of course, possible to buck the trend. Some people will do better than you would expect, and some people will do worse than you might expect when we start the new year. But roughly speaking, this value suggests that a linear model would be appropriate. Given that the linear model is appropriate, we can find the values of A and B for that linear model. I get 4.7 and 0.96, which means I can now write the equation of the line of best fit. It looks like this. Y equals 4.7, add 0.96x. And then the next bit, which is often the trickiest bit for students, interpret your values of A and B. Interpret suggests we should be doing something within the context of the mathematical model that we're dealing with. So what do A and B mean in terms of Year 12 and FA1 scores? Well, A is the easiest value to interpret because A is the y-intercept, which means it's the value of y when x is 0. X is the Year 12 score. So really what we're saying is when the Year 12 score is 0, or rather if, because we don't have a value of 0 on our table, so it's extrapolation, but the mathematical model suggests that if the Year 12 score was 0, then the Year 13 score would be 4.7%. And then the value of B we can interpret as well, but for this one we need to think a little more carefully. Since B is the gradient, we need to think about what gradient means in the context of Year 12 score and FA1 score. For every increase by 1 in the x direction, we would increase in the y direction by the gradient, whatever the gradient is. In this case, 0.96. So if your Year 12 score goes up by 1%, your FA1 score will be expected to go up by 0.96%. So pretty much 1-to-1. Roughly speaking, that's what we're talking about. So A is the score the model predicts a student will get in FA1 if they got 0 in Year 12, and B is the number of extra percent that a student will get in FA1 for each extra 1% they get in Year 12. To make the predictions for question parts A and B, the first one we're given a value for x and we're finding a value for y. And the second one is less commonly done because it feels like you're working backwards a little bit, but you could also theoretically work out what kind of Year 12 score a student might have had if they ended up getting 48% in FA1. All you need to do is substitute the appropriate values in for either x or y and take care that you choose the right one, and then you can work backwards and rearrange. So for part A, I get 43.1%, and for part B, I get 45.1%. It looks like, in general, we're saying that students who do very well at the beginning will do very well at the end, and students who do poorly at the beginning do poorly at the end. Roughly speaking, it's a 1-to-1 relationship, but there's a little bit of wiggle room in here because it's not exactly y equals x. There's a few other adjustments in there. Now, once you've tried exercise 4b, you can continue. There's a couple more slides where I'm going to look into a few other interesting things. Here's a bit of large data set analysis. I tried to find the strongest correlation example I could, and I came up with an ingenious idea. If we look at the wind direction and the gust direction, basically what that means is we're measuring the average direction that the wind is blowing throughout the day, and then we measure which direction the wind is blowing when it is blowing at its strongest. And it stands to reason that that should be a similar sort of direction. If it's blowing north-northeast all day, then when it happens to blow at its hardest, it's probably still blowing north-northeast. And that appears to mostly be what happens, and this data looks like an incredibly strong positive correlation. But you can see there's a few weird data points in there. There's some very strange ones going on. Almost all the data points seem to lie along a line which isn't even the line of best fit that's been indicated. Most of them seem to lie along a much better line of best fit, which would be somewhere going through 0, 0 really, something more like that. And yet those few data points that are trailing over here and over here, they seem to be messing up the whole thing, giving us a different line of best fit. Not only that, they're giving us a worse correlation coefficient than they otherwise would. It comes out pretty decent anyway, but it's going to be even better if we could somehow get rid of those points. A closer look at the data will help us see what's going on here. If you pause the video at this point and scan down the list, see if you can detect what the problem is and why we're getting such weird results for those extraneous bits of data on the top left and the bottom right. I'd recommend you pause and you give it a proper thought, and if you can't quite see it, give it a few more minutes. Keep looking at it, because you'll be kicking yourself if you have to wait until someone points it out to you. Alright, spoiler alert, I'm going to show you which row to look at. We want to look at this row here. We can identify this point on the graph if we look carefully. It's a point where the daily mean wind direction was just 10 degrees and the daily maximum gust direction was 350 degrees. They seem like they're very different numbers. And yet the cardinal direction, in other words, the one that you would just read off the compass rose, is north for both. So why do the numbers look so different? Well, 10 degrees just means 10 degrees clockwise of north, and 350 degrees means 350 degrees clockwise of north. But if you turn 350 degrees, then you'll find you could have saved yourself the effort by turning 10 degrees anti-clockwise. That's all that's happened here. Both of them are pretty much north. One is 10 degrees clockwise of north, and the other is 10 degrees anti-clockwise of north. So really, these numbers are not telling the whole story, or at the very least, the story is slightly disguised. If you can clean the data by coming up with a clever formula for adjusting them, you might be able to get a better fit on the graph. I'm not going to tell you exactly how to adjust it. You can have a think about what you might do with a direction of, say, 350 to adjust it so that it's more obvious that it's actually very close to 10 degrees. You might need some if statements in there somewhere. But if you can, you should end up with a graph that looks a bit more like this. So our data points now seem to match much more closely to a line of best fit that goes through the origin. It's a much, much stronger correlation, and although we have a few outliers there, those are the points that perhaps before we would barely have noticed as outliers. Things like this, yes, it's still there, but these really surprising ones that we noticed way up here, they seem to have been fixed. And by fixed, I mean moved. 350 has turned into -10. So it's actually not an anomalous data point at all anymore. It's very, very close to the line. Have a think about how you could do a similar thing. Maybe you can come up with these graphs for yourself. Just a quick plug for the large dataset calculator. If you Google this, LDS_calculator.xlsx, you'll be able to download it, or you can find it on LearnZone, or you can send me a direct message to get the link for it. You should have it somewhere. This is essentially the large dataset, but with a bonus sheet added on the beginning that lets you quickly and easily analyze data in different ways and pick out some general trends. This is the linear regression and correlation calculator. You can choose what data you want to investigate. All you need to do is change the values in this table up here. You'll be given the correlation coefficient, so you'll be able to see from the number how the data on the graph fits with the line on the graph. You can also see the gradient and the y-intercept in here, and you could even enter values to get predictions if you wanted to. When you get to year 13, when you're looking at the year 2 content rather, you will start to investigate the significance of a correlation value, which is essentially a way of saying how likely is it that the results would look as correlated as this, but actually there's just random chance behind it. There's also a few formulae down here. You can make use of these if you've got data that you're investigating in a spreadsheet, any spreadsheet, including the large data set, then correl for correlation, slope and intercept for the gradient and the y-intercept of a line of best fit. When you get to A-level Maths Year 2, here's a little precursor on what you'll be looking at. So in the right here, you can see we've got random data. You can see here, each of those values in the X and the Y column are just random numbers between 0 and 1. So there's no connection between them at all. But if you refresh the data often enough, then sooner or later, you're going to find that just randomly, they start to look a lot like they're following a straight line. Sometimes are very close to a straight line. And there is a way of measuring how likely it is that your data comes from random chance, and therefore a way of sort of ruling out things that might appear to have a correlation but don't, and making us more confident of the data that we're looking at. So instead of saying something like, well, there might be a link but we're not sure, we can now say with a relatively high level of confidence whether or not we think there is enough evidence that there is correlation or that there isn't correlation between two things. And the last thing I briefly want to mention is that product moment correlation coefficient only tells you about linear relationship. How well would a line fit the data? And in some cases, a line does not fit as well as you might think. This one's a bit of a strange one. If you look here, we've got 26 days and cases listed as essentially the Y values. If you plot this data, you'll find that you can calculate the product moment correlation coefficient, and it comes out at a whopping 0.868, which would probably count as good in anybody's book. But if you look at the graph, it tells a slightly different story. That straight line might be pretty close to the points, but just because the straight line is a good fit does not mean that the straight line is the best choice. It's clear that something else is going on behind the scenes here. And there's a technique you're going to learn about when we get to Year 2 statistics, where we will be able to take this sort of data and say, well, that straight line is not the best sort of model. Instead, maybe we can plot it with a curve. And if we can identify the kind of curve and apply similar techniques to what we've done with a straight line, then perhaps we can find an even better fit. Turns out that we can make this fit a 0.996 correlation, which is incredibly good. This, you might have guessed, this is data from the initial spread of coronavirus during the first 26 days of March in 2020 in the UK. And it's plausible that an exponential model is a sensible model to use here, because certainly initially, when the case numbers are low, the virus spreads exponentially. It will increase by something like 20% per day. So the number of cases increases by a fixed scale factor, which means you would expect it to follow an exponential curve. And it did for quite a long time. One other thing you can see here from towards the end of this graph is a little bit of hope creeping in potentially. It's only a few days, so it's not long enough to see whether this is just a temporary slowing down or whether it was something more. But even though we're getting more and more cases every day, even though it might be that the number of cases each day is, the number of new cases each day is still bigger than the number of new cases the day before, compared to the exponential model, we can start to see a reduction in the rate of increase, which is a bit more subtle than just a reduction in the number of cases. The number of cases is not reducing. It's not even a reduction in the number of new cases, because the number of new cases is still larger each day, but not as much larger as the exponential model might predict. So it suggests sort of the start of that leveling off that was about to happen. In general, there are a couple of different common models that we can work with. And one thing that you might notice about these, both the exponential one and the power law, is that there are only two constants that you need to find the value of. So there's something special about graphs like this, if it's possible to make use of certain mathematical techniques that you're going to learn to convert them into something more like a straight line, then the two values we get for the gradient and the y-intercept will be enough information for us to work backwards and calculate the size of the two values we need for this different kind of curve. And we can match, say, P and Q to a something X to the something type curve. Or we can match K and N to a K times N to the X type curve. So there's lots more scope and potential for this technique, but it all boils down to how we can match data to a straight line. And then mathematical trickery will allow us to convert non-linear data to linear data find a match with a straight line, and then convert the match straight line back into the other format. All this still to come.